Hey, I'm Sricharan from Chennai Mathematical Institute, and I'll be presenting our paper on Approximate Envy-Freeness for Indivisible Chores and Mixed Resources. So this is joint work with Umang and Rohit from TIFR. Let's begin. The setup we'll be looking at is the following. You have some items that you want to allocate to some agents, and the agents have some values for the items. For this talk, we'll just assume they are additive. So if an agent has value 10 for one item, value 20 for another item, and if you give both those items to that agent is going to have value 30 for the combined bundle. Right. And our question is, we want to allocate all the items to the agents, and we don't want to divide the items into smaller pieces. So we assume that the items are indivisible. And the question is how to do this fairly, how to allocate all the items in a fair manner. For this, we need to talk about notions of fairness. But before we do that, we'll just look at some applications of fair division of indivisible items. There are two kinds of setups we'll look at. One is when all the items are desirable, which you call as the good setting, and one where all the items are undesirable, which you call the chore setting. So for goods, you can think of allocating courses to students. So there are only limited number of seats for each course. You want to allocate the courses to students in a fair manner, or you want to divide the inheritance between the kids in a fair manner. So that's desirable items. Whereas for chores, you can think of dividing household tasks among roommates. You want to do this fairly, or dividing global emission responsibilities among countries in a fair manner. And so we need a notion of fairness to discuss this. One strong notion of fairness is that of envy-freeness. What does envy-freeness say? It says every agent should be happy with the bundle they have. So if you divide the items into bundles and you give me a bundle, should be happy with my bundle, and I should not look at someone else's bundle and think that has better value than the one I currently possess. Formally, what we want is my value for my own bundle should be at least as high as my value for any other agent's bundle. For example, if we take this instance, we'll just keep a running example for goods throughout, where you have three agents. Think of it as an adult, a boy, and a child. You have four items you want to divide among them. You want to divide a toffee, a ball, a car, and a watch among them. They have these given valuations for these items, and you want to ask if there is an envy-free allocation here. It turns out there is. If you give the car to the adult, you give the watch and the ball to the boy, and you give the toffee to the child, then the adult gets this. The adult is happy with the car. The adult is not going to envy anybody else's bundle. Similarly, the boy is happy with these two items. The boy is not going to envy the adult or the child. The child has value 7 for the toffee. It has value 3 for the boy's bundle. It has value 0 for the adult's bundle. So nobody envies anybody. This is an envy-free allocation. Does such an allocation always exist? Turns out that's not true, even in simple cases. If you just have a single item you want to allocate between two agents, then you can't find an envy-free allocation, because if you give the item to one agent, then the other agent has the empty bundle. So they are going to envy the agent who possesses an item, right? So even in simple cases, envy-free allocations don't exist, and even deciding if envy-free allocations exist is pretty difficult. So you can reduce partition to finding an envy-free allocation between two agents who have the same values for all the items even. So it doesn't always exist, and it's hard to even decide if an envy-free allocation exists. We want approximate notions of envy-freeness, one of which is envy-freeness up to one good. So this is a well-studied notion of fairness. For example, in course allocation that we discussed, EF1 allocations have been used. And what's envy-freeness up to one good? So EF1 allows for envy. So I might envy you, there can be envy, but my envy for you should vanish on dropping a single item from your bundle. So if you look at the example we had before, where there did not exist an EF1, where there did not exist an envy-free allocation, here there is an EF1 allocation, because if you give the toffee to the adult, then this is EF1, right? Because the boy envies the adult, but this envy vanishes on dropping the toffee from the adult's bundle. So EF1 allocations exist in this particular instance. It turns out even in general, EF1 allocations always exist and are computable in polynomial time using something called the envy cycle elimination algorithm. The idea is simple. You start with no items allocated. You allocate items one by one while making sure that at each step of the algorithm, the allocation remains EF1. You want to maintain this invariant. Let's start. Let's look at the algorithm on the same example as before. The envy cycle elimination algorithm has something called the envy graph, where the agents are the vertices of the graph, and this is a directed graph. So you're going to draw directed edges based on who's envying who at that particular allocation. Initially, no item is allocated, so there are no envy edges and the graph is empty. Start by allocating some item to someone. Let's say you give the toffee to the adult. Now, the boy and the child are going to envy the adult because they have nothing but the adult as the toffee. And this allocation is EF1 because this envy vanishes on removing the toffee, right? If you remove this toffee, this envy goes away and this envy goes away as well. And let's say we want to allocate the next item. Suppose we want to give the ball to somebody. Who do we give it to? You want to give it to some agent who is not envied by anybody else, right? So you want to give it to source vertices in the graph. So that will be our algorithm. Allocate new items to source vertices, that is source agents in the graph. This is going to preserve EF1 because any new envy created will vanish on dropping the last item that you gave somebody. So all the envy created by adding a new item to a source agent is going to be EF1. Right. So let's say you give the ball to the boy or the child. Let's say you give it to the child. Now the boy has nothing. So the boy is going to envy the other two people. Boy is a source vertex in this graph. Nobody envies the boy. So give the boy some item. Let's say some unallocated item. Let's say the car. Now you have an interesting situation where there's a cycle present in the envy graph, right? So in a cycle, everybody likes the item, likes the bundle they are pointing to. So A likes B's bundle, B likes C's bundle, and C likes A's bundle. What can you do here? There's one nice thing you can do, right? You can resolve this cycle by giving every agent the bundle they are pointing to in the cycle. So you can give B's bundle to A, you can give C's bundle to B, and you can give A's bundle to C, and everybody is going to become happier because they are getting a bundle they envy. The important thing is it doesn't just make the people in the cycle happier, it also preserves EF1. Why? The important part is noting that EF1 is evaluated with respect to envied agents bundles. So if I envy you, then as long as your entire bundle gets transferred to somebody, then my envy for you will just now transfer to my envy for the person who got your bundle. And if my envy for you was EF1 before by dropping a good from your bundle, because the bundle has just changed hands, now the new envy that I have for that agent is still going to be EF1 by dropping the same item. Okay. So because EF1 is evaluated with respect to envied agents bundles, EF1 is preserved by cycle resolution. And now what do you do? Now after resolving the cycle, there are no other cycles in the graph. So you still have the watch unallocated. You just give it to any agent and it's going to be EF1 because everybody is a source agent in this graph right now. Great. So the algorithm for fair good allocation is indivisible good allocation is simple. Whenever you have a cycle in the envy graph, you go and resolve the cycle by allocating items backwards. That preserves EF1. And once you do that, allocate new items, new goods to sources in the envy graph. That preserves EF1. How many times will you have to resolve cycles? it turns out you only need to do this polynomially many times, because every time you resolve a cycle, the number of NV edges present in the graph strictly goes down by at least 1, right? So you only do this polynomially many times, and you'll only need to add new items polynomially many times. So this algorithm runs quick, gives you a fair allocation of goods. What if you want to allocate undesirable items? What if you want to fairly allocate chores to agents? Again, you can't have envy-free allocations, right? Because if you just have one chore and you give it to me, then I'm going to envy everybody who doesn't have a chore. So if it's between two people, I'm going to envy the person who doesn't have a chore. So you can't have envy-free allocation of chores. So we'll need approximations, and the same a similar approximation, right? You define something called envy-freeness up to one chore, where now what will you have? Now I can envy you, so envy can be present, but that envy should vanish on dropping a chore from my own bundle. So it's the agent who envies who should be dropping a chore, because if you remove a chore from the envied agent's bundle, that's just going to make their valuation higher. That doesn't help us at all. So EF1 for chores is defined as any envy present should vanish on removing a chore from the envying agent's bundle. This causes some sort of asymmetry between EF1 for goods and chores, right? For goods, you're going to remove the good from the envied agent's bundle. For chores, you're going to remove the chore from the envious agent's bundle. This is a small difference, but something we should keep in mind. Why do we need to keep this in mind? Because the previous claim in literature basically said that if you run the same algorithm as earlier, the one you had for goods, but instead of allocating new items to sources in the graph, if you allocate new items to sinks in the graph, then this adaptation is going to give an EF1 allocation of chores. So that was the claim. It turns out that's not true. So let's take the instance mentioned here and see what happens when you run the naive adaptation. Just replace the word sources for sinks. So what you need to mainly look at is A's valuation here. So A has value -5 for the first chore, -2 for the next two, -1 for the last chore. So this is what we'll use to give a counterexample. So run the normal algorithm as before. Give A a chore, A envies two people, C is a sink, give C a chore. Now B is a sink, give B a chore. Now both C and B are sinks, give either of them a chore. Let's say you give C a chore. Now C has two chores, A has one chore, B has one chore. Now let's look at A's valuation for each of these items present, right? So A values A's own bundle at -5. A values C's bundle at -2 plus -2, which is -4. And A values B's bundle at -1. So A envies both of the other people. A has value -4 for this bundle, -1 for this bundle. Right? Now, when we just have goods, we can resolve any envy cycle that arises anytime and is going to preserve EF1. Let's see what happens when we try to resolve this envy cycle present here between A and C. So then A would get the two chores of C, and C would just get the single chore of A. Now A has these two chores and B has the same chore as before. Now my claim is, after resolving this cycle, the envy between A and B is not EF1. So this envy does not vanish on removing a chore from A. Why is that the case? Because A has two chores, both of value -2, right? And A's value for B's bundle is just -1. So if A drops this chore, A is still going to have value -2 for her own bundle and -1 for B's bundle. So A is still going to envy B after dropping this. Similarly, A will still envy B after dropping this as well, because A's value for her own bundle will still be -2, right? What has happened here? A earlier had a single chore of value -5, which guaranteed EF1. A swapped this for a bundle which had better value. So A's value for her bundle went up from -5 to -4. But resolving this arbitrary cycle caused a problem that now A's envy for B has stopped being EF1, right? So our problem was resolving cycles is not always going to preserve EF1 for the agents inside the cycle. For agents who are not part of the cycle swap, it's fine because they are still going to hold their same bundles and they'll still be able to lose the item that they earlier had. Why did we not have this problem for goods? Because for goods, you always evaluate envy with respect to the bundle you are envying, right? So in a cycle swap, it doesn't matter what new bundle you get as long as it has higher value. So as long as the new bundle you get has higher value, you're fine. You don't care what particular items it has. Whereas for chores, EF1 is going to be evaluated with respect to items you have in your bundle. So you need to be careful about what bundles you really want to get from other people in a cycle swap. And so we fix this by proposing a new algorithm based on the top trading envy graph. So instead of resolving arbitrary envy cycles that arise, we claim that if you resolve only top trading envy cycles, then this gives you an EF1 allocation. And it also runs in polynomial time, which is great. So what's the top trading envy graph? It's a subgraph of the original envy graph that you had, where instead of pointing to all the bundles you envy, you're only going to point to your most valued bundles. So in the envy graph, you just point to any bundle which has higher value than your own bundle, right? You don't do that here, but in the top trading envy graph, you only point to the bundle which you think has the highest value among all the bundles present in the envy graph totally. For example, here, what did we have? We had this cycle and we had a single edge from A to B, right? What is the top trading envy graph here? It's just the edges colored in red. Why? Because A had value -5 for its own bundle, had -4 for C's bundle and -1 for B's bundle, right? So A's value for C's bundle was higher than its own, but it was still not the highest. A still thinks B's bundle is the best among all the bundles present. So in the top trading envy graph, A only has an edge to B. A does not have an edge to C. In particular, it also says there are no top trading cycles, so you don't need to resolve anything here. You can just add new items to sinks in the graph without having to resolve cycles, which you might have to do in the case of goods, which you can do in the case of goods. Right? Okay, so what's the modified algorithm? It's very simple. It just says when there are cycles in the top trading graph, resolve them. And after you do this, allocate new items to sinks in the graph. You need to show two things for this to work. You need to show that resolving top trading cycles is enough. If you resolve top trading cycles, then there will always be a sink which is present in the graph. So this is simple to show. We won't go into this in this talk. The second thing is important. We say that resolving top trading cycles preserves EF1. Why is that so? The problem we had earlier was we might acquire new items in new bundles in cycle resolutions that are not good enough, right? It might have chores which does not help us satisfy EF1. So when will we be happy? Suppose we only resolve top trading cycles, then if I point to an agent in a top trading cycle and I receive their bundle, then because this was the highest valued bundle I had in the entire graph, I'm not going to envy anybody else after I get this, right? So after this, after resolving a cycle, everybody who's part of the cycle is going to be EF1. In fact, they are even not going to envy anybody. It's going to be envy free for agents inside the cycle after the cycle swap. Great. So, and we can also compute the top trading cycle graph in polynomial time. So now we get an EF1 allocation of chores in polynomial time using this algorithm. We only talked about additive valuations, but there's no reason to keep it additive. Even when the valuation of the chores is monotone, that is, it should just be non-positive marginal value for each bundle. It doesn't need to be the same value every time you add it to my bundle. So even in that case, it gives an EF1 allocation. And we also extended this to a nice set where you can have both goods and chores. And it's not just a global, these are goods, these are chores kind of setup, but each agent can partition it separately. So my idea of what's a good might be different from your idea of what's a good. So I might have a item which I consider a good, and you might consider the same item a chore. Even then we can get EF1 allocations by an extension of what we just discussed. So that's a pretty general setup where we were able to show existence of EF1 allocations. And you even compute these in polynomial time, which is great. There's also extension to a model with both divisible and indivisible resources. So you have divisible resources. You can talk about Envy-Freeness itself, right? You don't need to restrict yourself to Envy-Freeness up to one good. We only had this approximate idea of Envy-Freeness because we weren't able to divide the items into smaller pieces. So for divisible resources, you can have envy-free allocations. For indivisible resources, you want to talk about the notion of envy-freeness up to one good allocations. When you have both divisible and indivisible resources, you can define something called EFM, which is a combination of EF1 and EF, where it says every envy present should be EF1, but any agent to whom you give a desirable divisible resource, this we'll call a cake. So any agent who gets a cake should not be envied. So that is, if I envy somebody, they should not be given divisible desirable resource. Similarly, divisible undesirable resource, which we call bad cake, should not be given to any agents who envy others. So if I envy somebody, you shouldn't come and give me divisible undesirable resource. For this model, which was introduced by Bay et al. For goods plus cake setting, they showed the existence in this particular setting. We extended the definition to both desirable and undesirable. We were able to show existence and computation modulo a particular oracle when you have bad cake and both goods and chores. However, when you have indivisible chores and divisible cake, it still remains open. We were able to show existence in special cases, but not in the general case. Just to sum up, so the results that we had were fair allocations for chores using top trading cycles, fair allocations for goods plus chores using doubly monotone valuations, and fair allocation when you have both divisible and indivisible resource with both desirable and undesirable in each case, right? With just bad cake. So this, and there are a few open questions you can look at. For example, looking at the existence of EFM for that top right corner of the table, that's still open. EF1 for anything more general than doubly monotone, that's also open. So we showed the existence of EF1 for chores. However, EF1 plus Pareto optimality for chores is not known. So that's still an open problem. You know how to find it for goods in pseudo-polynomial time, but you don't even know the existence for chores. So that's one interesting line of attack. And that's all I wanted to talk about. So thank you.